Hello, everyone. This is Guang Yue from KOI Halligan Group in the Department of Physics in the University of Illinois at Urbana-Champaign. So today I'm going to talk about exploring parity transitions of Majorana bound state in the STIS lateral Josephson junctions. And here are my collaborators. Basically, the measurement is done at UIUC, and the bismuth solenoid sample is grown by Dr. Shanshik O group from Rutgers University. And here is the background and the motivation of my research. So start from particle physics. We have the Majorana Fermi, which is its own antiparticle. And in solid state physics, particles or quasi-particles could be governed by the Majorana equation. Such particles can be called the Majorana bound state. And the Majorana equation here is similar to the concept in the particle physics. The special part in solid state physics on the Majorana bound state is that it has a non-abelian property, which has potential application on the quantum computing area. So for example, we can have two pairs of Majorana bound state as shown by the blue curve here. And in such a system, each pair of the blue dot represents the parity state of the single electron. So if we exchange two Majorana bound state here, like the red curve described, we are actually changing the state of the system following by this formula. So basically, by exchange the position of the Majorana bound state in the system, we are actually doing quantum computing. In my research, I basically focus on the STIS Josephson device to study on the Majorana bound state. According to Fu and Kan theory here, the Majorana bound state can exist when you put an S-wave superconductor on top of a topological insulator, as shown in this picture, to form a Josephson junction. So whenever the phase across such Josephson device equals the odd number of pi, we can have a Majorana bound state enters the junction. And the current phase relation of the junction will have a sign favor 2 term. And based on the theory, we developed a model to calculate the critical current diffraction pattern of the STIS Josephson junction. So basically, we assume the current phase relation of such device using this formula. So the sin phi term is the regular Josephson effect, and the sin favor 2 term comes from the contribution of the Majorana bound state. And we also have a Gauss function here to localize the sin favor 2 term to be only around the odd number of pi phase. And the positive negative sign here are related to the parity state of the Majorana bound state. So if we plot this current phase relation, we will see the sin phi term is actually tiny spikes on top of the regular sin phi current phase relation. And using this current phase relation, we can calculate the critical current of the STIS Josephson junction at certain magnetic field using this formula. So basically, when you apply magnetic field on the area of the junction, like what is shown in this picture here, you can have a linear change of the phase across the junction along the y direction. And then you can sum up all the current to calculate the total current going through the junction. And we can find the maximum value as the critical current of the junction. And using this method, we can calculate the diffraction pattern of the STIS Josephson junction, which is shown by the red curve here. And the black curve is for comparison. It's a diffraction pattern of regular Josephson junction, which only have a sin phi current phase relation. The difference between the red and black curve is plotted in the bottom picture. So as you can see, based on our model, the diffraction pattern have certain features, which is due to the Majorana bound state. So the first feature I want to talk here is odd node lifting feature. So as you can see in the red curve, the odd node of the diffraction pattern are all lifted up, and at the same time, the even node of the diffraction pattern is still zero field current. So we call this feature the odd node lifting feature due to the Majorana bound state. And we can also observe another feature on the shoulder of the diffraction pattern. So when the magnetic field is large enough, we can have a tiny bump appeared on the shoulder of the diffraction pattern here. And we call this feature the anterior feature. So the field when this feature appears is when the Majorana bound state starts to come to the STS Josephson junction. And the third feature predicted by our model is called the bimodulation feature. So basically, due to the existence of the different sign of sine phi over 2 term in the current phase relation, we can have two types of washable potential for the Josephson junction. And then the junction can, if the parity of the Majorana bound state change, the junction can have a double field current. So next, I would like to talk about our measurement result, trying to confirm our model. So the colored picture shows a measurement of the dynamic resistance of the junction versus the base current and the magnetic field. We can extract the boundary between the blue and light blue area as the diffraction pattern of the STS Josephson junction into the black curve here, shown in this picture. So as you can see clearly in this measurement, the odd node of the diffraction pattern are lifted up. At the same time, the even node of the diffraction pattern is still zero field current. So basically in this measurement, we observed the node lifting feature. And for the anterior feature predicted by our model, we have done another measurement, and the diffraction pattern of the junction is plotted as a red curve here. And we also plot a black curve here, which is a regular diffraction pattern singularly due to the sine phi current phase relation. So as you can see, if we zoom in on the shoulder of the diffraction pattern, we get the bottom picture here. So basically at zero field, the diffraction pattern follows the regular shape of the sine phi current phase relation. But if the field is large enough, we start to see a tiny bump on the diffraction pattern, which is different from the black curve. So this indicates we have observed the anterior feature due to the existence of the Majorana bound state on the diffraction pattern. Next, I would like to talk about the measurement. We are trying to capture the third feature, the bimodulation feature of the STS Josephson junction. So basically, we measure the switching current distribution of such device. So in order to capture the double field current due to the sign change here, we need to ramp up the current through junction fast, just as the metastable state of the system can be captured in the measurement. So we build a measurement setup as shown in this picture here. So basically, we have an arbitrary waveform generator to apply current ramp through the Josephson junction. And then we have an FPGA-based data aggregation device to monitor the voltage across the junction. So we also set a voltage threshold. So whenever the voltage across the junction is above the threshold, we consider junction switch to the normal state, and then we can record the current going through the junction as the field current of the junction. So by ramp up the current multiple times, we can actually get the distribution of the field current of our devices. And here is one of the measurement results. So as you can see, at the zero field and the small magnetic field, we measured a pretty regular field current distribution, which is shown in these two pictures here. So it's basically a single peak and has certain asymmetry feature. And when the magnetic field is large enough and beyond the 30% of the flux quantum, which is actually around the anterior feature predicted by our model, in the measurement we see the critical current distribution becomes double peaked, and such feature also persists at a larger field here. So basically, this measurement seems to confirm our prediction, such that the STIS Josephson junction can have double critical current. And however, this result does not apply to all of our measurements and all of our devices. So here is measurement result on another device. So basically, as you can see, at all magnetic field, we only measured single peak critical current distribution. So this may due to a certain device, parity change of Majorana bond state only cause a small separation or small difference of the critical current, and they may be too small to be observed in the critical current distribution measurement. However, we can still, using this data, and we can plot the standard deviation of the distribution at a different magnetic field. We actually found some feature which may due to the Majorana bond state. So as you can see, in the same device of this measurement, we plot the standard deviation versus the magnetic field as the red curve here, and the black curve is measured the diffraction pattern of the device. This device is measured at a higher temperature, which is around 400 millikelvin. And the every curve of such device is no longer has a sharp jump; it only has a smooth every curve. Then basically, because our voltage threshold is fixed, when we increase the magnetic field, the every curve will move to the left of the screen, and the voltage threshold is actually sampling on different relative position of the every curve. And this so this phenomenon, this move of the every curve actually cause the standard deviation of the critical current distribution decay with the magnetic field as shown here. So this long range feature is simply due to the move of the every curve and the fixed voltage threshold. That should have nothing to do with the Majorana bond state. However, on the shoulder of the curve, around 30% flux quantum, we can see a tiny bump on the plot of the standard deviation versus field. So this may be due to the Majorana bond state, because this feature also corresponds to the anterior feature of our model. And when the Majorana bond state enters the system, we have double critical current, and we will have more noise measured. So the standard deviation will actually have a tiny bump here to slow down the long range decrease of the standard deviation. So this is basically all the measurements I would like to talk today. We also did some simulation to help analyze the data. So basically, we assume in the program the parity of the Majorana bond state will cause an instant change of the washboard potential, and we also assume a certain parity transition frequency of the Majorana bond state. Then basically, based on that, we calculate the critical current distribution, which is shown in these three pictures here. So as you can see, the shape of the critical current distribution is actually depending on the parity transition frequency of the Majorana bond state. If the transition frequency is low, we can have a clear double peak feature. And if the transition frequency is higher, we may have some intermediate feature here. And if the frequency is too large, we will have only a single peak critical current distribution. So basically, this simulation tells us the shape of the critical current distribution measurement. The shape of the critical current distribution actually depending on the parity transition frequency of the Majorana bond state. However, this is only a very preliminary simulation. So, for example, the middle picture looks similar to the data here. However, the separation between the two peaks is actually 10 times smaller compared with the measurement data. So we need to improve the simulation somehow to better fit the data. So here is another idea to simulate the current distribution. So instead of this slide, we assume an instant parity transition of the Majorana bound state. Instead of assuming that, we can assume the parity transition phenomenon is actually a gradual, smooth process. So whenever the parity of the Majorana bound state change, the washboard potential will not have an instant switch. It will have actually smoothly goes from one type of washboard potential to the other type. And if you assume such a smooth change with time, we can actually fit the data better. So this picture shows the fitting result, and fitted curve is the red curve. So as you can see, it can fit the data better because the separation between the two peaks is more close to the data. Again, this is also another preliminary simulation result where we need more data and more analyze to have some more conclusive result. So that's all of basically all the material for my presentation today. So here's the conclusion. So basically, we fabricate the STIS Josephson junction device, and the measurement on the diffraction pattern of such device shows the appearance feature and non-leaking feature, which seems to confirm our model and seems to be evidence of the Majorana bound state. And we also did some measurement like the current distribution measurement, trying to figure out the parity fluctuation property of the Majorana bound state. So these are really preliminary results, and we need more work and more simulation to be done to understand the data better and to have a more conclusive conclusion. I would like to thank these people for the help in my research. I would like to thank Nick Aubon, Suraj, and Professor Yuxuan Wang and Professor Smisa for the helpful discussion and for the work of simulation for our measurement. And I would like to thank my group members for the help. And I would like to also thank NSF to provide us funding. And if you have more questions, have some questions on my presentation, you can contact me by this email, or if you want to know more for our research, you can visit our group website here. Thanks.